Hello everyone, good evening. So this is physics 11th class. Myself Sandeep here. So I think we will start the lecture soon. So we'll wait for anyone to join. We'll give 1 minute. Hope everyone is doing good and happy new year to everyone. So can you hear me properly? क्या आप मुझे सुन सकते हैं? Just type in the chat box. That's good. And whether we are waiting for anyone or all students are present here. Okay, Suraj is left. Okay, so shall we wait for Suraj? Anyone has idea? Anyway, we will start and we will not uh, take much of your time because whether he will join or not. So yeah, let me present my screen to all of you. So can you see my screen? Yeah, let me know whenever you see my screen. Yeah, that's good. So I think last time we started with frame and inertial frame and non-inertial frame. Hopefully you guys do not have any question. If you have any question, you can ask here in chat box. Not an issue. Okay. So I think we finished here last time on the page number 50. So we will continue from there. So if you have any questions related to this Newton's law of motion or related to that topic, you can ask me. Okay, so let's go for next thing. So do you know the situation phenomena that can be explained using Newton's law of motion fall under Newtonian mechanics? Okay, so whichever physics which we can govern or we can write it down through the Newton's law of motion, it's fall under Newtonian mechanics. There are certain non-Newtonian mechanics also. So far, as our daily life situations are considered, Newtonian mechanics is perfectly applicable. So daily things like how fan rotates or what are the forces and everything. So that those things we can easily explain by this Newtonian mechanics. However, under certain several extreme conditions, we need to use some other theories. Okay, so there are limitation on Newton's law of motion. So Newton's law of motion is universal, but in one way it has limitations also. So Newton's laws are applicable only in the inertial frame of reference. Discussed later, right? We have discussed last time that inertial frame of reference. If the body is in a frame of reference of acceleration a, we need to use pseudo force, that is minus ma, right? In addition to all other forces, while writing the force equation. So along with other forces, we have to write the mass into acceleration also. That's we have seen that whenever we are considering inertial frame, we have to consider these other forces also. Uh, Newton's laws are applicable for point objects, right? So whenever there is point object, it is applicable. Otherwise, if it is like spherical or it has some volume, then it may not be applicable. So Newton's law is applicable to the rigid bodies. A body is said to be rigid if the relative distance between its particle do not change for any deforming force. So what does it mean by rigid body? So there is any body, and whenever it is in motion, it doesn't deform. So you might have seen small rubber type of balls, which when we throw here and there, it deforms, it changes shapes, right? So if it is changing the shape, then we can't apply the Newton's law here. So generally we are considering these are the rigid bodies, it doesn't deform under motion. So Newton's law, it doesn't hold very good for the non-rigid bodies. For objects moving with speeds comparable to that of light. Okay, so if suppose the object is moving at the speed of light, so that is very fast, then Newton's law of motion do not give results that match with experimental results, and Einstein's special theory of relativity has to be used. So what does it mean? So हमने देखा होगा कि अगर कोई भी object is moving with speed v, and speed is like light speed, it's too fast, you know. So anyone has the if so can anyone answer about how much time it takes sunlight to reach uh, from sun to earth? Anyone has idea? Can you write in the chat box? If you don't know, that's fine. Don't Google it or anything. Yeah, approximately 8 minutes. That's correct, Sankalam. So generally, so sun is like so much far away from our Earth, and it takes 8 minutes. So with the speed of light, right? So we can understand that speed of light. So anyone has an idea about what is the speed of light? It's it's 10 raised to 8 meter per second, right? So it is around, I do not remember exact value, but it is around same value. So it is so fast. So if it is so fast, the body is moving at such a high speed, then we can't use this Newton's law of motion. We may have to use this Einstein's special theory of relativity. Okay, so that is a very different topic, so we may not cover in 11th physics. So it may be for if you are going for advanced studies in physics, it may be useful. Then behavior and interaction of objects having atomic or molecular sizes cannot be explained by Newton's law of motion. So and quantum mechanics has to be used. So whenever we consider the, we know that we might have studied these atoms, right? This is center, and these are the electrons. Okay, let me clear all this. Okay, we might have seen this model where inside there is a proton, there is a proton, right? And around that there are electrons, right? This model we have studied. So if we want to study that, what is the speed of electron, or what is the forces interaction between this proton and electron, or there are neutrons also, right, at the center. So if we want to study those type of things, interaction between those electrons and protons and their behavior, their motions, then this Newtonian mechanics doesn't work, right? So we have to use the quantum mechanics. So that is a very advanced field of study, and nowadays people are using this quantum mechanics to study the uh, different type of things like quantum computing. You might have heard quantum computing is one of the fastest computing thing which scientists are studying nowadays. So there, this quantum mechanics is useful. Okay, and Newtonian mechanics doesn't work. So okay, a rocket in intergalactic space, okay, gravity free space between galaxies, with all its engines shut, it's closest to the ideal inertial frame. So we know that intergalactic, so in between the galaxies there is no force acting, no gravity force. Okay, so with all its engines shut down, so we can assume that one rocket is there and it is there, right, in intergalactic space between the two galaxies. So two galaxies are there. These are the two galaxies, right? Yeah, so I'm just showing the representation of galaxies. Galaxies are very huge. Okay, so we are just part of very small tiny part here. So we can you see this small point? That may be our Earth, right? In this galaxy, so it's huge. So in between these galaxies there is space. So if we consider that rocket with all its engines shut down, there is a rocket. And okay, let me, so this rocket is in between galactic space, and there is all engines shut down. However, Earth's acceleration in the reference of frame, the sun is so small that any frame attached to the Earth can be used as inertial frame for the any day-to-day situation in our laboratories. Okay, so so this is considered as ideal frame. Okay, and then for daily to day-to-day life, we can consider. We know that there is Earth acceleration in reference frame of the sun. So we know that there is sun and there is small Earth, right? So this is the sun. So if we consider, अगर हम जानना चाहते हैं कि क्या हो रहा है कि अगर ये अर्थ जो है वो भी इट्स मूविंग, राइट? अर्थ इज मूविंग. सो अर्थ एक्सीलरेशन इन रेफरेंस फ्रेम ऑफ सन, अगर हम लोग सन का रेफरेंस पकड़ते हैं तो यह अर्थ का मूवमेंट वेरी स्मॉल. ओके, so any frame attached to the earth can be used as inertial frame for any day-to-day situation. So हम लोग जो उस दिन हम लोग डिस्कस कर रहे थे कि कार का स्पीड, राइट? व्हाट इज द स्पीड ऑफ कार? तो स्पीड ऑफ कार मतलब अगर, let me clear all the drawings so that I will not confuse. So if we consider one car, okay, and we are considering this ground, right? Grounded as zero, but it is not at actually zero because Earth is moving. But for our day-to-day calculation, we can take it as a zero. We are not considering it as a moving with some speed, right? So if we say that this car is moving with 50 km/h, then we are considering the this ground ground speed is zero. Actually, Earth is moving, so this is not zero. But for day-to-day life calculations, all the laboratory situations, we are considering that as a zero. Okay, so this is the ये sentence यही कहना चाहता है. Okay, so ideal reference of frame will be the intergalactic space जहाँ कोई भी gravity force नहीं है, कुछ नहीं. That will be the ideal space. But हम day to day life में हम लोग ऐसा समझते हैं कि Earth is not moving, it is zero. Okay, and this holds very well, and a lot of calculation has been done on basis of that, and still everything is good, right? So let's move to the type of forces. Uh, अगर आपको कोई भी क्वेश्चन है, you can ask me. We will then I will try to answer your questions. If not, then I will move ahead. So till now we have learned about these laws of motion. Now we will uh, we will see that type of forces. So what are the type forces available in the natures, and how it can be used for the day-to-day life calculations. Okay. So we have studied, right, kinetics, and these are the dynamics. So in dynamics, what do? We consider these forces also. So if body is moving, what are the forces acting on that? So we are not considering only velocity, we are considering the forces acting on the body. So what are those forces? So all the forces in the nature are classified into four interaction, and that are termed as fundamental forces. So there are different forces, but for four fundamental forces are there. So that's we categorized, and we consider that as these are the four fundamentals. So for first is gravitational force. So it is let's see what is written here. It is attractive force between two point masses separated by distance. So what does it mean? अगर दो mass है, okay, any arbitrary bodies, so in between that and separated by distance, so इनका distance है, इनके बीच में क्या distance दूरी है, r, right? सो एनी टू बॉडीज, आप कोई भी दो बॉडी ले सकते हैं, और वो ऐसे है तो उनके बीच में जो अट्रैक्टिव फोर्स है उसे ग्रेविटेशनल फोर्स कहते हैं. सो मैग्नीट्यूड ऑफ ग्रेविटेशनल फोर्स बिटवीन पॉइंट मासेस, तो ये दो मास है, m1 और m2. सो उनके बीच में का जो फोर्स है सेपरेट बाय डिस्टेंस आर द इन बिटवीन दिस द फोर्स इज given as, this is gravitational force. So this is g. G is we can see the force is nothing but g into m1. M1 is mass of first body and mass of second body, divided by r square. R is distance between those bodies. So here g is the constant, like 6.67 into 10 raised to minus 11. Okay. So between the two point masses separated by a given distance, this is the weakest force having infinite range. So we can see that this gravitational force is not so um, a strong force, right? So we can see that from this number, right, 6.6 into 10 raised to minus 11. So we need something very very high mass, or and very very less distance, right? Then only we can say that force is really applicable, or force we can calculate. So to have very high forces which can be measured or quantified, or which we can use it for our day-to-day life calculations, so we need very very strong force, or strong masses, right? This mass should be very high, or distance should be very small. Then only we can consider this force, otherwise it is very weakest force. So this force is always attractive, so it never as a repulsive force. Okay. Structure of the universe is governed by this force. So we know that all planets and then stars, all those are governed by this uh, gravitational force. Common experience of this force of us is gravitational force exerted by Earth on us, which we call as at weight W. So we know that how much force is applied on us, right? So uh, we do not. So this is Earth, right? And considering, so considering we are standing here, right? I know this is not in proportion, but we can assume for this lecture. Uh, so this Earth uh, has a gravitational force which is felt by us. So if we try to put something on space, it will come down, right? So if we put here something, it will come down. So that is due to gravity. We have seen that in famous Newton's story about gravity. Like he has seen that apple coming down of the tree, and he found that okay, there is gravitational force, right? So this is the same gravitational force we are calculating, and we consider W as a weight of our body is due to this gravitational force. So how does we calculate? So if we consider G m into m, we know the mass of Earth and we know the radius. So we consider that this is the radius, right? Radius of Earth. So this is the main point from where we are getting the attractive forces on our body. So if we put, we know the radius, we know the mass of Earth. So we can see here, mass of Earth is so high, right? 6 into 10 raised to 24, and the distance is also very high. So due to this, we can feel that gravitational force. So if we jump from the table, we may not be means we are not floating in the air, right? We will come down on the ground. So why? Because of this gravitational force. So we can consider, because when we jump from the table, so there are two bodies or two mass points, right? One is us, like what person is there, and one is this Earth. So in between that, whatever the distance, we can see there is attractive force, and that due to that attractive force, we come down. Okay. So generally, whatever the mass is there, we convert it into the uh, we convert into the I mean, by multiplying the acceleration, we convert it into the force attracted on us. So we generally calculate in the Newton. Okay, that we can convert into the kg and all this stuff. But yeah, mass is in kg, and this weight is in Newton. Okay, so here what we feel this force only due to the normal reaction from the surface of our contact with Earth. Okay, so we generally exhibit, or we feel these type of forces only due to normal reaction from the surface. So this is the normal reaction. Okay, due to this force, we consider that we are getting some attractive force, and we will come down, and we are attached to the Earth, right? We are not going to the space. So you might have seen in the pictures, movies, that how these rockets has been launched, and so generally there is that's you will come to know, and maybe this physics, or maybe in 12th, that how what is the velocity if any rocket is moving around this Earth, and at certain distance, and if it has velocity, and at particular distance, due to this reaction forces, already we talked about this, right? Attractive force between the two bodies, and if it is moving, then at some point it may come out. So this is the technique generally we use for sending the rockets to the Mars, or any other things. Okay, so that's we will learn, not in this lecture, but maybe afterwards. So generally, whenever the rocket goes from the Earth, it will have some velocity, and it will move around the Earth at certain velocity, right? And if this distance is more than the critical distance, right, from the Earth, so suppose this is R, right, and RC, then this, and if it is moving at the velocity v, and this is more than the RC, then this rocket will go outside the gravitational force of this Earth, and there will be no gravitational force from the Earth, and it will go to the space, right? So this way, generally we send the rocket towards the different planets, or to study the different different stars. Okay, so that is different study itself. We will learn if it comes in this syllabus. Uh, okay, so there is attractive force between the body, like us, the persons, human, and the earth, right? And that's we have tried to quantify it. So all individual bodies also exert gravitational force on each other. So whenever there are two persons, so they also exert some forces, right? So there are two point masses. So suppose, for example, mutual gravitational force between two sumo wrestlers. So we have seen the sumo wrestlers. Sumo wrestlers क्या होते हैं कि जब भी रेसलिंग करते हैं, या हमने ये WWF या यहाँ देखा होगा, तो ये सुमो रेसलर्स, सो जनरली उनका क्या रहता है, वेट 300 केजीज, अराउंड 300 केजी। और अगर हम लोग सोचेंगे कि वो 0.5 मीटर, मतलब 500 मीटर पे एक दूसरे से 0.5 मीटर, 0.5 मीटर पे अगर एक दूसरे से दूर खड़े हैं, तो व्हाट विल बी द फोर्स बिटवीन देम? सो considering all the values, it's 24 micronewton. So we can see that how much small force they are exhibiting on each other. So for general calculations, we can neglect such a small force or small weight. Okay, so considering the, see, 300 kg is their mass. So consider their force acting on them, right? On sumo, on each sumo, it's acting around 3000 newton, and compared to that 24 micronewton. So we can neglect such type of force. So whenever there are two bodies, like between two persons, there are some attractive force, right, due to this gravitational force. But uh, we neglect because it is too small to consider for our general applications. So general, like whatever the body mass of general people, like 60 kg, right? So if we consider 60 kg, so force is 600 newton, then also it is too small to consider 24 micronewton. Okay, so generally we do not consider the uh, gravitational force between the two bodies, different bodies, if mass is so small. Okay, let's go to the another force, uh, that is electromagnetic force. So it is an attractive or repulsive force. So this is not only attractive, it can be a repulsive also, between electrically charged particles. Okay, earlier electric and magnetic forces were thought to be independent. Earlier they were considering electric and magnetic both are the different forces. Okay, so after demonstration of Michael Faraday and James Clerk Maxwell, so these are two great scientists. Michael Faraday was generally experimentalist. So he used to do all the experiments and try to put all the theories. Whereas Maxwell is famous for making those experimental to the mathematical equations. Uh, but generally, Michael Faraday means Michael Faraday was a great scientist with a due respect to him. He has not gone beyond the algebraic equations, like we might have seen like quadratic equations or cubic equations, right? Like x square plus 2x or something like that, or trigonometry, something sine cos theta. He could not put it in the differential equations. So, but James Clerk's Maxwell, he's another great scientist. He continued the work of Michael Faraday, and he has contributed a lot of equations. So, one of the great scientists for the electromagnetic force is Maxwell, because he could put all into the mathematical equations, and those equations holds really good for all real-time applications. That's the contributions he had. uh, Generally means it's not so means it's generally it is talked in the scientific community that Newton, Einstein, and Maxwell, they are the greatest scientists and they have contributed a lot to the physics. So if you want to, whenever you, mean, so this is my suggestions to you all. अगर आप if you come across such names of scientists, so please go and study their profile. You know that in Google you can quickly go through their profile, what they have done, what they have contributed. I know some of their terms is may not like what they have contributed. So for that, some terms may not be yeah, some terms may be difficult to understand at this point of time, but you can see their profile or where they studied, what was their fundamental thinking, how they grown up, right? So all those things may be useful for you. So whenever you see a name of such scientist, because there are many scientists from last many centuries, right? So you can see their lifespan. So Michael Faraday's were around 200 years from now, 220 to 30 years he born. Then Maxwell is around 170 years, 190 years, right? So see there like 190 years back they born and they come up with these theories, and uh, they have very limited information available, right? So not so much internet or nothing, right? And they do not have calculators or computers. They used to do all this by their hands. So it was such a difficult time, but then also they come up with such great theories and great equations, which still we are using for our applications or scientific advancement. So whenever you come across such type of scientist name, just Google it and try to read their profile. That is very one good exercise. That is my suggestions. Because out of the box also we have to study like out of syllabus. So okay, so we will come to our syllabus like electromagnetic force. Electric and magnetic force are unified through the theory of electromagnetism. So uh, due to electricity there is magnetism, and due to magnetism there is electricity. So this way we can combine the electromagnetism and we can unify this theory. These forces are stronger than gravitational force. So electromagnetic force are stronger than gravitational force. Our life is practically governed by these forces. Majority of forces experienced in our daily life, such as force of friction, normal reaction, tension in spring, everything you take is sorry. Okay, so everything you consider around us, like reaction force, spring and tension force. So for a prima facie, you may think like, oh, tension in spring is electromagnetic force. So you may think like, oh, this may not be right. But prima facie, you may see that if you stretch the spring, आप अगर spring say खींचते हैं, तो you experience that force. So how it is that electromagnetic force. So if you come down to the atomic level, so we can term in terms of electromagnetic force. So atoms or molecules कैसे behave कर रहे हैं, तो we can define in terms of this electromagnetic force. So everything we can bring it down to the atomic level or molecular level, and we can show that okay, uh, at last everything is electromagnetic force. Okay, so under the action of these forces, there is deformation object that changes intermolecular distance, thereby resulting into a reaction force. Okay. So क्या होता है कि अंडर द एक्शन ऑफ दिस फोर्सेस, जो इलेक्ट्रोमैग्नेटिक फोर्सेस है उसके एक्शन से देर आर सम डिफॉर्मेशन. So suppose there is liquid, okay, and liquid and if we apply some electromagnetic force, so this is one of the famous experiment. If we put the electric coils around this pot, and this is liquid, right? So due to this electricity, this liquid will also change intermolecular distance, and it will also rotate. Okay, so this is the action by this force, and this will be rotated. They are changing their intermolecular distance and getting rotated. So these are the reaction force, right? So we can term literally anything in terms of this electromagnetic force, and we can see that how action and reactions are taking place. So another force is nuclear force. So this is a nuclear force. This strong nuclear force. There are two nuclear forces and weak nuclear force. So this is the strongest nuclear force that binds nucleons together inside a nucleus. So till now we have studied the in our physics that about atomic model, right? So uh, at the center there is always neutrons and protons, right? And outside there is orbit of electrons, right? Those we have studied till now. So at the this center, or this is called nucleus. Okay, so at nucleus there is nucleons is nothing but what? Neutron and proton. So they are hold together, right? They can't go out of this nucleus. So holding force to these nucleons is strong, and this is the strongest. So this strong nuclear force binds this together, and it is a very short range. So we can consider that at very small level. So we do not see that force, or we do not feel that force. It is so at such a small distance, 10 raised to minus 14 meter. So you can think of very small distance at which this acts, right? So therefore it is very strong, attractive force, and is charged independent, and it is not dependent on the charge. Whereas this different forces depend on the charges, but this nuclear force, strong nuclear force, do not depend on the charge. So what is meant by weak nuclear force? This is the interaction between subatomic particles that is responsible for the radioactive decay of atoms. So generally what happens in particular beta emission. So this nuclear force is there, right? Strong nuclear force. So what happens that there is subatomic particles. So between the interaction between this electron, neutron, and proton, so there is beta decay. Okay, and so these forces, like these weak nuclear forces, what does it do? So it tries to move out of these beta particles, right? So the reason these beta particles are coming out is weak nuclear force. So weak nuclear force is not a gravitational force, but such weaker than strong nuclear, but much weaker than the strong nuclear and electromagnetic force. But these force, weak nuclear force, are much weaker than this strong nuclear force as well as electromagnetic force. So generally range is like 10 raised to minus 16 meter. So it attracts in between very small distance, already strong nuclear forces were acting around 10 raised to minus 14 meter, but this weak nuclear force acts around 10 raised to minus 16 meter. Okay, if you have any question about these forces, you can ask here. So they have given a small example about weak interaction force. So this radioactive isotope C13 is carbon 13 is converted to nitrogen 14, in which a neutron is converted into proton. So we have seen that neutrons are inside the nucleus, right? It converts into the proton. The property is used for the carbon dating to determine the age of the sample. So this carbon dating is generally used for the age of sample. Like suppose we have seen the trees around us, right? And we want to check their age, like from uh, what time they are here. So generally they take small part of the tree and they carry out this carbon dating. So we and from that they understand their age. So not only for this, so we might have seen that for excavation, so for historical uh, archival people, so what they do, they dig it, like we might have seen Mohenjo-daro or those type of stuff. There they find some very old stuff, like or way old dinosaurs, animals, stuff we see around the world. So what they do, they take this bone sample and they carry out this carbon dating. So for that purpose, this radioactive isotope C13 is converted to N14 for the carbon dating. So, in radioactive beta decay, the nucleus emits electron or positron. Okay, so from nucleus they emits some electron, an uncharged particle called neutrino. Okay, so in beta decay, what happens? One electron and uncharged particle called neutrino is emitted. Therefore, there are two types: beta decay, beta positive, and beta negative. During beta negative, a proton is converted into neutron accompanied by the positron emission. And during beta negative decay, a neutron is converted into proton accompanied by the electron emission. Okay, so we know that there are beta decays. One is beta positive and beta negative. In beta positive decay, proton inside the nucleus is converted to neutron, whereas in beta negative decay, neutron is converted to proton. Okay, so we know that nucleus is always consist of proton and neutron. So for different decay, one in one decay proton is converted to neutron and another neutron is converted to proton, and this way beta decay takes place. So another most interesting illustration of the weak forces is fusion reaction in the core of sun. So during this, protons are converted into neutrons and neutrinos is emitted due to energy balance. In general, emission of neutrino is evidence that there is conversion of proton into neutron or neutron into proton. This is possible only due to weak forces. So what happens? We know that there are protons inside the nucleus, right? This is the atom nucleus, and there are some proton and there are some neutron. Neutron, I will. Okay. So due to this weak interaction forces, so what happens? These neutrons convert to the proton, or proton converts to the neutrons, and due to this, they means weak interaction force. It converts to the different means proton to the neutron and neutron to the proton, and this releases energy. Okay, so we have seen during this proton are converted to neutron and neutron is emitted due to energy balance, and it releases some energy, and this is the energy. We have seen what happens at the sun, and it releases energy, and this energy comes to us in form of light, like sunlight. So we know that these are the weak forces, how this is important for the fusion reaction. So anyone knows that there is experiment going on, or we can say that people are trying to build an reactor based on this fusion reaction. So in around us, we know that these nuclear forces are converted to the for energy use, right? So there are two types. One is fission, another is fusion. So fission we have seen already. Uh, in there are many power plants which converts these fission reactions to the energy, and which energy we can convert it to electricity, and that's what we are using in our daily home to home. So but there are another fusion reactor. There is not such a large scale fusion reactor available, but in Europe, it's Tokomoko energy reactor. Uh, People are trying to build a fusion based nuclear power reactor, where they are trying to, so what they generally do, whatever the energy they are getting, their energy is nothing but in terms of heat. Okay, so they will try to boil the water. Okay, so from boiled water what will happen, there is some, it will generate it to the vapor, right? And this vapor they try to push it on the turbine. Turbine is nothing but we might have seen the windmills, right? Pawan chakki. So it's same, something like same. So this vapor goes on this turbines, and this turbines moves. So if this turbines moves under magnetic, these are the magnets, right? So if this turbine is moved, rotated, then we get the electricity. So this is general principle. So from fusion or fission, right? So right now fission is available. uh, Most of the world is using fission reactors, and people are trying to get fusion as another alternative energy source where they can convert it to the electricity. So for that, these weak interaction forces are useful, or weak interaction forces are really advantageous. That's the whole story. Okay. uh, if you have any question, you can. So one question for you guys. So where do we observe this electromagnetic force in day to day life? I want general thing. So there is Wi-Fi, right? Or okay, there is phones. So the signals, like whenever we talk to one person to another person, so there are some electromagnetic forces, right? Those, so electromagnetic spectrum is there, we can say. And we day to day life we observe those type of stuff. Another example is mm, fan, right? So fan also works under the electromagnetic principle. So this electricity is converted into magnetism, and it rotates to the fan. So there are different stuff which are governed by the electromagnetic force in day-to-day life. And generally, weak interaction force or nuclear force are not uh, applicable for us at this point of time, because we are not considering it at the subatomic particle level. But when we are designing a system, and a nuclear reactor or nuclear fusion or fission reactor, then this type of things are really important. Okay, so we will quickly go through this example, 4.2. So in this example, they have mentioned that three identical point masses are fixed symmetrically. So these are the 3 point masses A, B, C on the periphery of circle. Obtain the resultant gravitational force on any point mass at the center of circle. So this is point mass at the center. Okay, extending this idea to more than three identical masses symmetrically located on the periphery. How far can extend this concept? So I will quickly go through this example so that we can understand what's happening here. So figure below shows three identical point mass, right? These are M are 3 point masses at the periphery of the circle of radius r. mass m at the center of mass to these masses are attractive and are directed as shown. So there are three different forces: FMA, FMB, FMC. Okay, so these are three forces. So we know that by this formula GMM divided by R square, we can resolve those forces, or we can calculate these forces. Forces FMB, forces FMB, and MC are resolved along FMA, right? In this direction, and components perpendicular to FMA cancel each other. So components along FMA are FMB cos 60 and FMC cos 60 is equal to half MH. So these are the forces get cancelled each other because their magnitude is same and their direction is opposite, right? So this resultant is 0. Resultant force on M is 0. So totally resultant force on the this M is 0. So generally what happens? So if we resolve these forces, so this FMC, there will be two components, like one is this, one is up and one down. So any force, we have the two components, right? So if theta, and this is the F, so this is F cos theta, F cos theta, and this is F sin theta. So any force, if it is making an angle with respect to our reference, okay. So here reference is this is a reference, right? We can take it as a reference. So this is the force. This is exactly vertical with this axis. So we are not resolving it. We do not have to make it this f cos theta or sin theta. We do not have to take two components. But considering this, right, MC, FMC, so it is making an angle, right? We can show you, right? And it is making angle with theta. So what will come here? It's FMC. Okay. So okay. So you can resolve in any direction here. So they have taken theta in this direction. Okay, this is theta for them, or 60. So FMC sine 60 will come here. That is this force. And FMC cos 60 will come this force, right? So we resolve the FMC. Similarly, if you take FMB, so it will have two component. So they are taking FMB and this as a theta here, or 60 degree. So FMB cos 60 is this. So this is general for any type force resolving. So if F is here in making theta, so this horizontal component along with this theta will come as F cos theta, and along this vertical direction on another direction F sin theta. So similarly we resolve these two forces. So these two forces will be balanced by this force, right? FMA. And these two forces cancels each other. So resultant force on the mass M is 0. That is the conclusion from this figure. Okay. Uh, let's go to the next thing. So for any even number of equal masses, so if instead of 3, if equal masses are there, force due to any mass M is balanced by the diametrically opposite mass. So instead of 3, if we take 4, so diametrically opposite forces will cancel each other. So for any number of odd masses as seen of 3, the components perpendicular to one of them cancel each other, while the components parallel to one of these add up to in such a way that resultant is 0. So here also we have seen the, if the number of masses are odd, then also it cancel each other in different way, but it will cancel each other and there will be no resultant force on the M. So if we take even number or odd number, it will cancel out and the resultant force on the M will be 0. Okay. So as the number of masses tends to infinity, so suppose there are a lot of mass, I mean different points masses are there. The shape approaches to the circumference of circle. So there are different masses, so it will considered as a circle, right? Circular ring. So in circular ring, though it is circular ring, due to this masses at resultant force and the center will be 0. Okay. The force exerted by ring mass on each mass at the center is 0. So that's what we have concluded from this uh, exercise or example. So in three dimensional, if we consider this in three dimension, it will become a sphere, right? So instead of circle, there will be sphere, like small ball we can consider, and there are infinite number of masses around that ball. But the gravitational force for any mass kept at the center of hollow sphere is also 0. So that's what they want to show it here, that at any um point in the center, the resultant is 0. So my question, I need an answer from the next lecture, that if suppose it is not at the center, then whether it is more forces or less forces on any ring. Okay, suppose there is a ring, and instead of keeping it center, I keep it here somewhere. So what will be the forces? Means it increases, decreases, whatever the answer. Just give me the answer. Next lecture, I will ask you again about that problem. And till then, you can take care, and happy new year. Have a great evening. Okay, see you next time. Thank you.